This is the very last full video for the elementary statistics class. And in this video, we're going to be doing the very last hypothesis test for the course. And that is the hypothesis test for analysis of variance, or often said ANOVA. So in particular, we're going to be starting out with talking about the F distribution. And we have already talked about the normal distribution, the t distribution, the chi-square distribution. Each of those are for different hypothesis tests. But for the one we're doing today, we're going to be using a different one called the F distribution. Then we'll get into ANOVA. And in particular, there's one-way ANOVA, there's also two-way ANOVA, multi-way ANOVA. We're going to get into one-way ANOVA, which is the ANOVA that we do for this elementary statistics class. And that is going to help us understand if many populations all have the same population mean, okay? Or we're actually going to find out if they don't have the population mean, it's all the same. And that will be what ANOVA, or one-way ANOVA, is all about. Then after that, we're going to finish off the whole course, and we're going to do what's the most important piece of all of statistics, at least in my opinion, and that is deciding what kind of hypothesis test or what kind of confidence interval. First, is it a hypothesis test or is it a confidence interval we're interested in? And then once you've decided that, which type is it? Are we talking about a chi-squared? Are we talking about two different population proportions that we're comparing? Or ANOVA that we're doing today? There's many, many kinds of confidence intervals and hypothesis tests that's happened in this class. So I'm going to kind of do a recap of all the different tests and how you decide which one to use. Okay, or should you use a confidence interval, and then which confidence interval to use. So let's jump into the F distribution. So we've already talked about many distributions in this class. Again, normal, students t, chi-squared, binomial. Well, there's another one, and that's called the F distribution. And that's the distribution we're going to use for this last hypothesis test we're going to be doing in this class. And if you remember, the t distribution and the chi-square distribution had degrees of freedom. And depending on the degrees of freedom, you get a slightly different curve. Same thing with the F distribution, but it turns out there's actually two different types of degrees of freedom, two different numbers, and depending on what combination of those two numbers you get a different curve. And those numbers are called the numerator and the denominator degrees of freedom. So if, for example, you have 3, 5, that's this one here, and it's, you'll see, very much skewed to the right. Whereas if you had 50-50, that looks very normal. I'm not going to get into the details of the equations or anything other than letting you know that there is this distribution called the F distribution. So the test statistic for an ANOVA test will be the F test. Also, just like you've had before, when you calculate that test statistic, you place it on the x-axis, and then if you look at the area to the right under the curve, that's going to be the p-value. And if the p-value is small, you reject the null hypothesis and accept the alternative hypothesis. Same thing we've done for every other hypothesis test. It's the same idea. So now let's get into ANOVA. And in particular, we're doing one-way ANOVA in this class. There's a two-way ANOVA, there's others, but for this class, since it's elementary statistics, we're doing one-way ANOVA. And ANOVA stands for analysis of variance. That's a little bit misleading because you might think, well, does that mean you're going to decide whether the variances are different? Absolutely not. What we're going to be looking at with analysis of variance is to decide whether 3 or more population means are the same So do the three populations have the same population mean? So you might want to look at, again, weights of people in the United States in different states. And that won't be 3, that would be 50. So you're going to have H naught is the means are all the same. Population mean is mu. We've seen that many, many times. And when you have many, you usually use subscripts. So mu sub 1 equals mu sub 2 equals, and then you keep going until you got into that last one, mu sub n. So this could just go to 3 sometimes. If you're doing states in America, it would go to 50. So however many populations you're comparing, that's how many mu's you will have. Then there's H1, and you have to be very careful about H1 because a lot of people think that the complement of all of the means being equal is all of the means being different, but that's not true. So for example, if you looked at the first 10 means and they were all the same, and then all of a sudden you got to that 11th mean and it was different, and then all the rest are the same, then most of them are the same, but there's 2 of them are different. So H1 is at least 2 population means differ. So again, many could be the same, but as long as there's 2 of them that you can identify that are different from each other, that means that H1 is true. So the nice thing is it's always going to be basically the same. Notice I use symbols for H naught. Mu1 equals mu2 dot 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 equals mu n. And I use words for H1. It's easier to use words. Can be done in symbols for H1, but it's easier to use words. So for one-way ANOVA, just like all the other hypothesis tests and confidence intervals, there were some requirements, okay? Something you had to have in order to do that. The first one we've seen before, and that is normality. So we saw, for example, to do a t-test, you had to have a normal distribution for the sampling distribution, okay? Or to do a two-sample independent t-test, same thing. Yeah, had to have that normal distribution. Well, it's no different. If you have a one-way ANOVA, we have to make sure all population distributions are approximately normal. We've seen it before. Now we're doing it again. So each of the many, it could be many this time. The next one, which we really haven't seen before, is that all populations have the same standard deviations, or at least not too different if the sample sizes are nearly equal. What we're not going to get into, because that would be advanced statistics, is how do you decide what it means to be not too different? And there are hypothesis tests for that. I'm not going into it, but if you take an advanced statistics class, you'll be able to verify or say that they're not the same, or say there isn't evidence to show they're not the same. But for this class, just note that you just got to have the same standard deviations or close to the same to be able to do ANOVA. The next requirement is the requirement that has to be true of every single hypothesis test, every single confidence interval, every single thing we do in statistics. And that means that when you collect your data, you have to do it without bias. If you have bias, then your sample is not going to represent the population, and it's pointless. On the other hand, if you have simple random sampling, or if you have a sampling technique that prevents as much bias as you could possibly get, so it's really not too bad, then we can do ANOVA. So we got to make sure that we have a representative sample. Then we also have to make sure the samples are independent of each other. So for example, if we're doing a survey question, and if people are asked 5 different questions, each with quantitative variables, then that wouldn't be independent because it's one person answering 5 different questions, and that would be dependent. So this is really for comparing many populations and population means when they're different populations, not the answer to this many questions from the same person type of thing. So the samples must be independent of each other. And then finally, the categorization of the sample is done in the same way. What that really means in the real world is that, let's say you were doing a study about people's weights in America, like I mentioned, and you did it all over the country. You're probably going to hire a team, maybe one person from every state, and you're going to have them do the sample in each of the states. The most important thing is before you start, you have a meeting. Could be on Zoom, whatever, and you have a meeting and you say, hey, this is how we're going to ask the question, and this is how we're going to deal with the questions that might be asked by the people that we're asking, and we're going to make sure that we're all on board with the same method and process. So that's what I mean by the categorization of the sample is done in the same way. It just means that you don't treat one group differently than the other. So let's take a look at an example. And the examples of following are the mean driving speeds the same for Highway 50, Highway 89, and Pioneer Trail. So just let you know, if I live in Tahoe, and those are kind of our three main fast roads that we've got, and we want to find out, do people drive the same speeds? So let's pretend that we did a survey, or maybe we clocked a bunch of cars, and this is what we got. On Highway 50, we see a bunch of speeds. Same thing with Highway 89. Same thing with Pioneer Trail. Notice that we are looking at three different populations. They're independent of each other. And we're looking at quantitative data. The data is all numbers, clearly. And we want to find out if the population means are all the same. That's what ANOVA is all about. So now let's perform the hypothesis tests. And just like you're used to, we always start out with the null hypothesis. The null hypothesis is H naught colon, you're used to that. And then with ANOVA, it's all the populations means equal to each other. So mu1 equals mu2 equals mu3, where mu1 is the population mean driving speed on Highway 50. Mu2 is the population mean driving speed on Highway 89. And mu3 is the population mean driving speed on Pioneer Trail. And then we do H1, and we use the wording that we saw before, and that is that at least two population mean speeds differ. We don't know if it's Highway 50 and Pioneer Trail different. Maybe 89 and 50 are the same, but 89 and Pioneer Trail are different. We don't know, but if at least two of them mean speeds differ, or the population mean speeds differ, then we get to say H1 is true. So the next step is what you're used to. We've got our H naught, we got our H1, we have our data, and we put it into the calculator. So let's go to the calculator. Here's the calculator. We're at the very, very end of this whole class. It is the last hypothesis test we are going to do. So we go to the very bottom, and we'll see the last one says ANOVA. I click on ANOVA, and it says enter the data values separated by commas. Okay, and then hit calculate, and the F statistic and p-value will be generated for you. So we have data 1, data 2, data 3, data 4, all the way down. And I'm going to save you the time of watching me do it. I actually put the data in and separated by commas. So our three different highway driving speeds collections of data. And then I scroll down to the bottom, and I hit calculate. That's it. Our test statistic is F, and that is 1.924. Our p-value is 0.17488. You should be used to this by now. We look at this p-value, and this p-value is large. 0.17 is bigger than any level of significance that you would ever use. And hopefully at this point in the class, since we're at the very end, when you see a very high p-value, we know to fail to reject the null hypothesis. Let's go back and write down the final conclusion for this example. We failed to reject H naught, and hopefully we can say there is insufficient evidence. You can also say there is statistically insignificant evidence. Those mean exactly the same thing. To conclude that the population mean speeds on the 3 roads are not the same. That's all there is to analysis of variance. Of course, there's all these requirements, and I'm not going to get into whether they're true or not for this example. I don't know if we have a normal distribution for each of these. We got small sample sizes, so if we don't, then this was worthless. I also have no idea if the standard deviations are the same. So there's a lot of things you'll have to do when you get into your advanced statistics class. Let's look at another example. And that is a study was done to see if the mean GPAs for in-state, out-of-state, and foreign students are different. What can be concluded at the 0.01 level of significance? And we have a table here, in-state, out-of-state, and foreign, and GPAs of these students. And as I've mentioned before, we can use ANOVA if all the requirements are met. We are comparing 3 population means, so that's not the problem. But who knows, again, if we have a normal distribution, who knows if we have the same standard deviation or variances. There's a lot of things that we got to deal with. Again, we didn't talk about whether or not this data was collected using random sampling, but we're just going to make the assumption that everything works. And then we state our null and alternative hypotheses. And H naught is mu1 equals mu2 equals mu3. Population mean for in-state equals the population mean for out-of-state equals the population mean for foreign students. And we're talking about the mean GPAs. And then H1 is at least 2 population mean GPAs differ. That's all there is to it. We have our H naught and we have our H1. Sometimes you'll also say that type of student is a factor in GPA. It's another way of wording the H1. So you'll hear that sometimes in certain courses in your upper division courses. So I want to let you know you'll hear it that way sometimes also. So we got our null, we got our alternative hypotheses, we have our data. Let's go to the calculator. Here's the calculator again, and I saved some time and I put in the data. So we have the GPA separated by commas for data 1, data 2, data 3, in-state, out-of-state, and foreign. And I just scroll down and I hit calculate. And there's our test statistic, which is F equals 13.54. And the p-value is very small, 0.0001. So we have a very small p-value. So this time we get to reject the null hypothesis. Let's go back and interpret. All right, we got a very small p-value. We reject H naught, and there is statistically significant evidence to conclude that at least 2 of the population mean GPAs differ. We can also say that type of student is a factor in mean GPA. So let's do one last example. This will be the very last hypothesis test that we do for all of these full videos for the entire course. And here it is. How long will you live? You as in this cute little dog. Okay, and the question is, are the mean lifespans for dogs the same for different living conditions? So we can imagine that they went and they tracked a bunch of dogs that lived in a fenced yard, a bunch of dogs that always are indoor, they never are let outside, then a bunch of dogs that are mix of indoor and outdoor. Then you got stray dogs. And the question is the population mean lifespan the same? So let's write down H naught and write down H1. H naught, in this case, we have 4 different populations. So H naught is mu1 equals mu2 equals mu3 equals mu4. And then H1 is at least 2 population mean lifespans differ. That's all there is to it. It's always pretty much the same. So again, we're going to have to make all kinds of assumptions, and I'm just going to go with it. And let's jump to the calculator, and let's find the test statistic, and let's find the p-value. Here's the calculator again, and I put in the data of how long these dogs lived in the 4 different types of living conditions. And I just scroll down to the bottom. I hit calculate, and there's our F, 2.0989, and our p-value 0.13. And by now we see when we have 0.13, that's bigger than any level of significance we'd use. So that means we failed to reject. So let's go back and interpret. We can conclude that there is insufficient evidence to conclude that the population mean lifespan for the 4 dog lifestyles differ. And I want to remind you, when you have insufficient evidence, it does not tell us that the population mean lifespans are the same. And in fact, in this particular situation, for indoor-outdoor, for example, we have a sample size of 5. So hopefully, you know by now, you should never do statistics with a sample size of 5 for any category. So in particular, probably the reason why we have insufficient evidence is that the sample sizes are too small. Maybe there is a big difference in mean lifespan, but we don't know from such a small sample size. It's just too hard to tell. It might be that they really are different, but our sample sizes are small, or it might mean that they're not different. We just don't know. And hopefully you know for hypothesis tests, when you fail to reject the null hypothesis, that just means you don't know. It does not mean that H1 is false. You can't say anything, basically. So it's fancy ways of saying that we don't know anything. That is the very last hypothesis test we have for this entire class. But there is one more thing I want to do, and that is kind of summarize everything we've been doing with confidence intervals and hypothesis tests. And the main piece is if you are given a question or if you want to do some research, you have to know, do you want a confidence interval or do you want a hypothesis test? Which one is relevant? You also have to know which type of confidence interval and which type of hypothesis test you need to use. So let's do some summary. So do you want a confidence interval or do you want a hypothesis test? Let's start there. So in particular, if you want to estimate a mean or estimate a proportion or a difference between means or a difference between proportions, or if you want to find the lower and upper bound of the interval, then we're looking for a confidence interval. On the other hand, if we're asked the question, is the mean or proportion less, more, or different? So if that is our interest, is there a difference in these population means, or is this population proportion different than what it was last year? Okay, or is the distribution different? That's another one too, from what we would expect. Then we're talking a hypothesis test. It's very important you understand the difference between the two. Those were the two main concepts of much of this course. So then the next thing is, what situation are you in? What type of confidence interval or what type of hypothesis test? So let me go through the different types. So the question is what test to use or what interval to use. What type are we going to be doing? Or which calculator button do you want to use? So first thing, if you have qualitative data, then at least for this course, we're going to be using a chi-squared test. And there were 3 different chi-squared tests. The first one was called the test for independence. And that was when we wanted to find the relationship between categories. Okay, so we have 2 different qualitative variables. And we want to say, is one variable independent of the other variable? Or is one related to the other? Is there a relationship between the two? If you know about one of them, does that help you understand the other? All of these questions are about tests for independence. Then there was, do we have the same distribution as a known distribution? So often that is the distribution uniform? Is the distribution normal? Or is the distribution the same as some maybe big distribution we already know about? Like, we know about what's happening in all of the United States. How about our town that no one's done research in? That's going to be a goodness of fit to see if the distribution is the same as some known distribution. And then the final chi-squared is when we have 2 different distributions, or we're seeing if 2 different populations have the same distribution or different distributions. And we don't know either of the distributions, so we're going to take a sample from both and then compare to see if the distributions are the same or are they not the same. And that was the test for homogeneity. Next, if we just have one sample taken, you should always be thinking about that. Are we just taking one sample? Is it just one survey question? Is it just one population? That's the one sample. If it is a yes-no question and it's just one sample, and you have to have NP and NQ greater than 5, then we do a hypothesis test for a proportion. Okay, if it's a hypothesis test. If it's a confidence interval, of course, you do a confidence interval for a proportion, just a single proportion. On the other hand, if it's a quantitative question, and you also have to have n greater than 30, or you have to have a normal distribution, then we're talking about a hypothesis test for a mean if we're doing a test. Of course, if it's a confidence interval, we'll do a confidence interval for a population mean. So always ask yourself, think about the survey question. I like to imagine me asking the question to my best friend. And I think about, how am I going to word the question? And then I'm going to say, how is my best friend going to answer that question? And what comes out of that person's lips? If it's a number, then that means it's quantitative. If it's yes, it's a yes-no question, or no is a yes-no question. So we always want to think about what the survey question is and what all the different people are going to say. Or if you're going to be doing an observation of 40 different, I don't know, weather reports. Well, are we looking at a bunch of numbers, or are we looking at a bunch of yes-nos? That's the important thing. Not what the overall idea is, but what will the data look like when you have many data values? Are they going to be yes-nos or numbers? So next, if you have 2 samples. So now we have 2 samples, and that could be either done via having 2 different populations, and you're going to ask each of the groups, you're going to take a sample from each population, and you're going to do a survey for each sample, okay, or an observation and some calculation for each of the two samples. It could also be 2 survey questions, but 2 samples. If we're going to be predicting y given x, so if we want to find out what's our best prediction for maybe the second survey question's answer, if we know the first survey question's answer, okay, is there a relationship? If one goes up, does the other go up? If one goes down, does it go down? Or maybe vice versa, okay? We have to also assume that for any given value of x, the distribution of all the y values for that given value of x is a normal distribution. And in that case, we do regression analysis. And that's where you have an equation of a regression line, a slope, and a y-intercept. You have an r, you have an r squared, and then you also have a hypothesis test that says rho equals 0 for h naught and rho not equal to 0 for h1. On the other hand, if we have 2 samples, and for the 2 samples, each of them are yes-no questions, and we have NP and NQ greater than 5 for both of the groups, then we're talking 2 proportions. And again, that could be a confidence interval for the difference between 2 proportions, or it could be a hypothesis test for the difference between the 2 proportions. Either way, it's going to be 2 proportions. On the other hand, if we have the difference between 2 dependent, often called paired, quantitative variables, and we also have to have the NDiff, or we got to say the total sample size, okay? So it's not how many people necessarily you sampled, but how many differences there are. It has to be greater than 30. And if that's the case, we're talking about 2 dependent samples. And again, that could be a hypothesis test for 2 dependent samples or a confidence interval for 2 dependent samples. The next situation you could be in is a situation where we have 2 independent samples. So that's kind of when you have 2 different populations. You're going to take a sample from the first population, a sample from the second population, and there's people in the first population have nothing to do with those in the second population. There's just a group of this and a group of that. Okay, and it doesn't have to be people, but it could be whatever you're observing. And if we're talking about a quantitative question, and we also have to have both sample sizes greater than 30, or we have to have normal distributions, then we're going to do 2 independent samples. And that could be a hypothesis test for 2 independent samples, or a confidence interval for 2 independent samples. And then the final test that we did in this course, the very last one, was today. And that is when you have more than 2 samples, such that you have quantitative survey questions. There were many assumptions, which I'm not going to get into the assumptions, but we talked about them earlier in this video. So if you happen to have multiple samples, more than 2 usually, and they're quantitative, and we want to find out if the population means are all the same, then we do analysis of variance, or ANOVA. So again, the very most important thing in this entire course is to be able to look at the research you're going to do, or the question that's being asked, and know whether you're going to do a confidence interval or a hypothesis test. And then once you know which one, then which type are you going to have to do? And once you know which type you're going to have to perform, then you just go through the steps, go to the calculator, find the test statistic and p-value, and state your conclusion, either with a confidence interval or with a hypothesis test. That's what most of statistics is all about. So I hope that you got some valuable information from this full collection of videos. And I wish you success as you finish this class off, and also success in your academic career as you use statistics to fully analyze whatever you're doing in your upper division coursework, okay, or graduate coursework, or fully analyze what you're doing in your career, or maybe just fully analyze what you read in the news or whatever's going on. So hopefully you understand how essential it is to understand statistics to truly get what's going on. So thank you again for watching these videos. And this is the very last video, and I wish you success.